Hi, welcome again to this lecture. Uh, Myself, Dr. Abid Pradhan, Assistant Professor, Department of Mathematics, School of Basic and Applied Sciences, Adamas University. So, in the last lecture, we have talked about the basic set theories. So, we have talked about the definition, subset, and equality of the sets. Then we have talked about the null set, universal set, some points or notes on that. And then we have seen the operations on the set, and we have discussed about the operations on set by using some example. Now we'll talk about the operations on the set uh, by visualizing things. So the tool which is used to visualize the operations on the set is called Venn diagram. So let me just first take the Venn diagram. Like I'm taking the universal set as U, this as U, and I'm taking two sets A and B like this. This is A, this is B. Now, let us try to understand what do you mean by A union B by using the Venn diagram. So, in the universal set, A or B, two subsets of universal set. So, whenever we talk about the universal set, any set is the subset of universal set. So if I think about the A union B, it represents all the elements which belongs to either A or B. So that means this thing, all the elements from A and B will represent A union B. This is my A union B. Now, if I think about the A intersection B, so this is the Venn diagram of the that represent the Venn diagram of the A union B. Now let us think about the A intersection B. What do you mean by that? Let us try to understand A intersection B. So this is my A set, this is my B set. So what is the A intersection B? A intersection B is going to be this common portion of A and B. This is my universal set. A and B are both subsets of the universal set. So here the intersection part, that is the common part of A and B, this will represent the A intersection B. This is my intersection. Now, what do you mean by the complement? So, if I take the Venn diagram here, the universal set is A, and this is my A set. Then the A complement is going to be this whole part which does not belongs to the set A and belongs to B. That means, sorry, belongs to universal set. So that means excluding this A, whatever the elements are there in the universal set, it represent the A complement. Okay. So A union B means all the elements which are in A and B both, means whenever we consider the or, means either in A or in B. Now, if I think about the intersection, then there are the common elements, the elements which are in the common portion of A and B. And the A complement means the elements which does not belongs to A but belongs to the universal set. So that is the shaded region of this shaded region here. Now, let us try to understand what do you mean by the relative difference. So if I think about, say, this is my universal set. Now, if I consider the set A and set B here, this is my A set, this is my B set. So if I think about A minus B, that means the elements of A but not of B. So if I think about the A minus B, this is this portion, this shaded portion is my A minus B. Similarly, if I think about the B minus A, that is going to be the elements of this B which does not belongs to A. That means this portion is there. So let me draw that thing here. So If I consider this as the universal set, this is my A set, this is my B set. So B minus A is going to be this one. If I consider this is A, this is B, then this portion is B minus A. Now, if I think about the symmetric difference of A and B, so it is like the elements of A and B, either of A or B, which is not in the common portion of A and B. So this is A symmetric difference B. So this is the thing. So here the elements of A, only A, the elements of only B, they are the symmetric difference. They will be the means. I can take this as I mentioned in the last class or last lecture also, that this is A union B minus A intersection B. This you can think as exactly one of A and B. Exactly one of A and B. In that case, we represent that by the symmetric difference. Okay. So let us go for the some rules of the or algebra of set theory. Okay. So here, let me remove these things. Okay. So there are certain rules of set theory. Here we are going to discuss about that thing. The first rule of set theory is commutative law. Commutative law means if I take union of two sets A and B, then A union B will be same as B union A. So let us verify that thing. So if I consider A is equal to suppose or equal to 1, 2, 3, B equal to suppose minus 1, 0, 1. Then what will be A union B? A union B is going to be minus 1, 0, 1, 2, and 3. So if I take B union A, that will be obviously same thing. Okay. So that is called commutative thing. So if I take the similarly, if I take the intersection, it is going to be uh, 1 only. So we have uh, B intersection A, which is also again 1. That means it is holding this commutative law. So commutative law says that if I uh, use the union or intersection, which is the operation on the set, if I take the union or intersection on two sets, the order we are doing the operation, it does not matter. So if I take A union B, that will be the same as the B union A. And similarly for the intersection also. Okay. The next law is the associativity or associative law. Associative law says that if I have three events or three sets A, B, and C, then if I take the union of these three sets, then in which order we are taking the union, it does not matter. That means A union B union C will be same as A union B union C. So here we are taking the union of B and C first, and then we are taking the union of A with this new set B union C. And in the right hand side, we are taking first the union of A and B, and then we are means we are taking the union of this new set union B with the C. So here this associativity says that they will be the same set. They are representing the same set. That means this whether you are taking the union of B and C first, it does not matter. Similarly, for the intersection also, if I take the intersection of B and C first and then take the intersection of this new set or with A, the set whatever we are creating here left on the left hand side, that will be same as the set if I take first intersection between the sets A and B and then we are taking the intersection with C. They will have the same elements. So these two sets are representing the same sets. So the associativity is very clear. Commutative means the order of appearance of the event or the state does not matter in this operation. Whereas in this associative law, the order means how we are operating. If the operations are same for all the sets, then how we are operating in which manner, it does not matter. So A union B union C will be equal to A union B union C. Okay, like real numbers. If I take 1 plus 2 plus 3, whatever the result we will have, that will be equal to 1 plus 2 plus 3. That will be the same thing. So that is the associativity. Okay. The next thing is a very important rule which is called distributive law. Distributive law is like this is the distribution of union over intersection. So we are taking union of A with B intersection. So on whatever we have here, that will be the same as in union of A and B intersection union of B and C. So here this union is distributing over the intersection. So first I have to take A union B and then intersection is there. So that's why intersection will come here. So A union C will come here. Similarly, in the next we have the distribution of intersection over union. So basically you look into the order of how we are taking it. So A intersection B union C, that will be equal to A intersection B union A intersection C. So this union, whatever we have in the bracket, that will be the second operation. First, I have to do the intersection because we are taking intersection of A with the new set B union C. Okay, so you can very easily verify this thing. So let me take A equal to, very quickly we are going to do this thing. Suppose A equal to 1 2, B equal to suppose minus 1 1, and C equal to suppose 2 and 4. So what will be A union B intersection C? So if I look into, let me just change this set. It will be, suppose I'm taking this as 2 minus 1. Okay, so A union B intersection C, A union A is equal to 1 2, B union C. So if I look into this thing, this will be equal to B intersection C is equal to minus 1. So this will be equal to minus 1. Okay, so we are going to verify this distribution now. So I'm taking A is equal to 1 2, B equal to minus 1 1, C equal to minus 1 2. So if I take A union B intersection C, that is going to be 1 2 and minus 1, because B intersection C is equal to minus 1. So if I take A union B intersection C, A is equal to 1 and 2. So I will have this thing. Now let us check the right hand side. So if I take A union B, that is going to be minus 1 1 2, and if I take A union C, that is going to be uh, minus 1 1 2 again. Okay, so A union B intersection A union B, A union C, that will be equal to the same set minus 1, 1, 2. So it's very easy to verify. You can check it. So for the similarly for the next rule, where the distribution of the intersection over union, that is same thing where it is following here also. Okay, you can very easily verify it like this. You can take very simple sets of 2 or 3 elements and verify that it is holding. And if you want to prove it, you can prove it by taking some elements and show that the left hand side is a subset of the right hand side, and then right hand side is the subset of the left hand side, so that we can show that the both the seeds are subset of each other. We have already seen in the first lecture that two sets will be identical or equal if they are subset of each other. Okay. So the next law is that complementary law. Complementary law means here if I take the union of the set with its complement, then it will give you the whole universal set. We have already seen that thing from the very beginning of, or the from the definition, from the definition of the uh, complement of a set. We have already seen that a complement is equal to nothing but the relative difference of A with the universal set. So if I take the union of the set with its complement, it will give the universal set S. And also we know that there is no common element between the set and its complement set. So A intersection A complement is going to be the null set phi. Okay. So it's very clear here that if I take the union of the set and its complement, it will give the universal set S. And if I take the intersection of them, it will give you the null set or phi. So here I have already mentioned this rule, actually difference rule, that A minus B is equal to A intersection B complement. Already we have seen this thing. Involution rule, that is if I take the complement of the complement set, that will give you the set itself. You know that it's very straightforward, that if I take the complement of the complement set, that means if I take the complement of a set A, it is representing the set excluding the set A itself. Now if I take the complement of that set, it will actually excluding the A complement, that means A itself. Okay, that is the involution law. And the next law is the idempotency law. That means if I take the union or intersection of the set with itself, so if I take the union of the set with itself, that will represent the set itself. And if I take the intersection also, it will represent the same set, same set. Okay. So the next law is the very important one, which is called De Morgan's law. De Morgan's law says that if I take the complement of the union, it will be the intersection of the complement of individual events. So that means if I have A union B whole complement, that will represent A complement intersection B complement. So look into this notation. Here we have union in the De Morgan's law, it changed to intersection whenever we are taking the complement. Now similarly, if I take A intersection B whole complement, it will give you A complement union B complement. So it's very straightforward. You can prove it very easily. If you want to verify it, you can do it there. So these are the basic things of set theory, which is required to study the basic probability theory. So we are in a position somehow to study the basic definitions of probability theory. So let us go to that part. So we'll start with the definition of sigma algebra or sigma field. So before going to the before giving the uh, formal definition of the probability theory, let us define what do you mean by the sigma algebra or sigma field. Sigma algebra or sigma field is a collection or class. So, as you know, collection means it's a set. So we know that set means it's a collection of well-defined objects. So to construct a sigma algebra or sigma field, first we have to have a collection of sets. So it's a collection or it's a set of sets. Is said to be the sigma field or sigma algebra script S if the elements of script S satisfy the following property. So I have a set of sets which satisfy certain property, then we call that set as a sigma algebra or sigma field. It's a structure. Now, what are those properties? The first property says that the null set should belongs to the that collection. So the first one is that null set or phi, which way I'm representing by phi, it belongs to that collection. Second property says that if I have a set A in the collection, then its complement must be there. Okay. And the third thing says that if I have a countable union of sets belongs to the collection, then if I take the union of those sets, it must belongs to the collection. Okay. So if we accumulate these three things, then how the structure look like? So it's like if I have a collection of sets, then the null set must be a element of that collection. And if I consider any element of the collection, then its complement must belongs to that set. Okay. And if I have some sequence of uh, sets in the collection, then if I take it's an infinite sequence for the time being, then if I take the union of those sets, that union also belongs to that collection. Now, let me give an example in a finite case. Here, in the third, we have a infinite collection of sets. But instead of taking that, let me take a very simple example of a finite case. Suppose I have script S that is equal to first rule. If I want to construct the sigma algebra, the first rule says that the null set should be an element of the set. That means if null set belongs to S, this null set should be belongs to S. The second rule says that if I have a set belongs to the collection, then its complement must be there. Now, if I think about a set, if I think about a set S, then I'm considering that says the set as the universal set. Suppose, then what will be the complement of this null set? Complement of the null set is going to be the set itself. So I must have that set here. So if I consider the set S and I'm trying to construct a sigma algebra around that set S, then the collection should start with the null set and the set itself. And then we'll consider all the possible subsets of S. This will construct the collection which will be a sigma algebra. So let me take a very simple example. Suppose I am taking a set like S, or let me take a very different example. Suppose different notation. Suppose E equal to a set like 1, 2, 3. Okay. And we want to construct a sigma algebra corresponding to this A. So the sigma algebra is going to be the null set E, as I already mentioned, and its complement, which is the set itself, E. Then all the possible subsets of E. That means I have to consider the singleton set 1, singleton set 2, singleton set 3, singleton set, sorry, elements of 1 2, 1 3, 2 3. So these are the possible subsets, the possible subsets of E. So A's contain the sets which are subset of E. So it contains the phi, it contains the set itself, it contains the all possible subsets of E. So we already mentioned that this kind of set is called the powered set of E. So if I have a set E which is a finite set, that means there are finite number of elements in the set, then we can construct the sigma algebra very easily. If I consider the power set of the set, then that will be the sigma algebra corresponding to E. Okay, so I hope this is clear. Then let me go to the next section in which we will actually define what do you mean by the probability. So in the probability, we can actually define the probability by using the axiomatic definition. So if I want to define the probability, then probability is a measure actually. To define the probability, we need to know about some basic definitions like what is experiment, because the probability is related to some experiment. We have to know about what is the random experiment, and then we will talk about what is the sample space, and then we can define the definition of probability. So in the next lecture, we'll talk about these few things. Till then, see you.